Hello everyone. Today I'm going to talk about thermodynamics and fluids, an introduction to these topics, which are related to one another, especially because when we're dealing with thermodynamics, we're dealing with the study of heat, and heat is energy, and energy exists in matter. And now, if matter is not a solid, if it's a liquid or a gas, it can also be seen as a fluid. So that's why I decided to make one video for both. So basically, um, we have the universe, we have the cosmos, we have particles bouncing on each other, we have exchange of energy, transference of momentum during collision. So there's in the cosmos, there's constantly something going on like that. And energy cannot be created nor destroyed, only transformed. And energy can obtain multiple forms, as can be seen in all of the complexities that we see around us. So, there are three laws for thermodynamics, and there is a zeroth law of thermodynamics. Well, if an object A is in thermal equilibrium with object B, meaning they have the same temperature, and object B is also in thermal equilibrium with object C, then that means A and C are also in thermal equilibrium. That makes sense. If A and B are in equilibrium and B is in equilibrium with C, then A and C are also in equilibrium. So this is the zeroth law of thermodynamics. The next law is the first, is that energy cannot be created nor destroyed, only transformed. You cannot have energy out of nothing. You simply cannot have an entire universe for nothing, which, well, they say there was nothing and then there was everything. But I think if you think about it like this, maybe the only time where things came out of nothing was at a creation at the Big Bang. Because any time after that, the energy that there is in the beginning is conserved and is just transferred into its multiple forms. So energy in itself cannot be destroyed. There's always recycling going on. The universe recycles the energy that it has and generates new forms of matter and states, quantum states, and so forth. Number two, entropy in the universe is always increasing. So the universe was very simple in the beginning, and it's growing more complex and complex. If you have a container with gas in it, and you open the container in an empty room, initially there's more organization, uh, there's less entropy, there's less disorder because the gas only occupies the space within the volume of the container. And as you release the gas in the room, the gas expands, so the disorder increases. There's more entropy as the gas expands. So the universe is in fact expanding and in growing complexity since the beginning. So the entropy will always increase. And the third law says that the entropy at absolute zero is zero, meaning if there's no temperature, then there's nothing moving, there's no disorder. Um, okay, now when we're talking about, uh, especially in thermodynamics, when we're talking about gases, in real world, things are much more complicated. In the real world, things are very complex. So, but physicists use ideal cases to help uh, to help uh, or understanding, because in reality things are much more complex. We just assume ideal cases so the math can be more simplified, so that everything can be more easier to understand with simple equations. In reality, equations are just approximations, because in reality things are a lot more complex. So what defines an ideal gas is that gas particles are point-like with no volume, meaning if they occupy a container, their volume is point-like, like it's negligible compared to the size of the container. And the reason for that is at the moment that you have a gas particle too big compared to the size of the container, uh, you have issues with the fact that you have to consider the geometry of the particle, the geometry of the gas particle, and because gas particles may not just be one atom, may be two bounded to each other. So it really depends. So if we neglect the volume of the gas particle and if we assume it's just a point line, it solves a lot of our problems. Like we don't have to deal with anything like that. Second one is collisions between particles are elastic, meaning when they collide, there's conservation of of energy. Like they don't lose energy during collision, and it's perfectly elastic because when particles collide, they there's a time during collision. It's the time from which there is the impulse. If that's instantaneous, okay, no energy is lost. But if the collision lasts for a while, some energy is lost. And and that could complicate the matter a lot. That could complicate the usage of our equation. So what we do is we consider the collisions elastic, meaning they're instantaneous. Like the collision doesn't last any bit of second or millisecond. It's just instantaneous, so that way energy is not lost. There are no intermolecular forces between gas particles. Remember when we talked about gases being point-like? We also don't want gas particles to be attracting one another because we want them to be as random as possible without forces between them and the container. And the fourth one is gas particles move at random. We want the gas particles to move at random because if one side of a container is hotter than the other, so it's not perfectly at random because there's a transfer of energy. But if we assume that that gas particles move at random, that solves also a lot of the problems because we don't have to deal with one side of the volume of the gas moving different than the other. Then we had to use that in our equation, which would make it too complicated. Gases in the real world approach an ideal gas when at higher temperatures and lower pressure. Why is that? Lower pressure because if gases are point-like, there's less pressure, there's less force per area as they hit the walls of the container because they're small. Now, higher temperatures is because we want the collisions to be elastic. So they hit the walls of the container and they bounce off, or they hit each other elastically and briefly without transferring or energy or without losing energy. So all the gases can approach an ideal gas, approach, because the ideal gases don't exist at lower pressure and higher temperatures. Okay. Um, now, we know that pressure is force per area. So if you exert the same amount of force in a smaller area, you increase the pressure. Or if you exert the same amount of force in a bigger area, you have less pressure. That happens when you have a needle, like you try to poke yourself with a pen, nothing happens. But if you do it with a needle, you poke yourself because needle you're exerting the same force in a smaller area. So that increases the pressure. Now, um, so what we have is that assuming ideal gas, we can use the equation PV equals nRT, where P is the pressure in pascals, V is volume in meters cubed, N is the number of moles of a gas, R is the gas constant, and T is the temperature in Kelvin. So you can use that equation to know what happens. Like if you increase the volume, what happens to pressure? Assuming temperature is the same, if you increase the volume, pressure goes down because there's more room to expand and there's less pressure. If you decrease the volume, you increase the pressure because particles are hitting each other more often. Um, when you apply heat to a material, um, you may increase its temperature uh, Q is the amount of energy that you put in the material. C is the specific heat capacity of the material at a given temperature and pressure. And delta T is the amount of is the change in temperature in kelvins. Now, when a material is undergoing a phase change, when there's a phase change of the material, the temperature doesn't change, but their energy can be absorbed or released during the phase change, while temperature itself is not the same. Is the same. Uh, Temperature doesn't necessarily mean energy, uh, because you can have a large pool that is cold, have more energy than a hot coffee inside a coffee cup, uh, because energy is also proportional to mass. According to Einstein's equation, E equals mc squared. So the more mass you have, the more energy you have as well. So when there's a phase change, you use the equation Q equals mL, where L is the latent heat of the material. If it's uh, vaporizing or condensing or melting or freezing, it's going to have different latent heats for each between two phases. Solid to liquid will not have the same latent heats as liquid to gas, and so forth. The first law of thermodynamics implies that the change in internal energy of a gas is equal to the heat absorbed or released minus the work done by the gas. Um, so there's many things that could happen. You could have an isothermal reaction where the volume may change, but the temperature does not. You can have other types of change, such as isobaric, when there's the same pressure. The work during the isobaric process is the pressure times the change in volume. You also have an adiabatic process where no heat flows in or out. That means Q is zero, but the change in internal energy will just be equal to the negative of the work. There's also isochoric, where there's no volume change, meaning the work is zero. If there's no volume, change in volume for a gas, the work will be zero. You can find the root mean square velocity of molecules in ideal gas with the equation square root of 3 RT over molar mass, where R is the gas constant. This equation is derived from 1/2 mv squared equals 3/2 nRT. What does that mean is that if you solve this equation, molar mass means mass per mole. So technically, if you solve this equation for V, you're gonna have uh, you're gonna have the mass per mole at the bottom of the equation and so forth, and you get the root mean square velocity. What does the root mean square velocity mean? The gas particles in a gas, they all travel at different speeds, mostly. But there is a root mean square average, like an average for all the, the velocities, because in any room, in any place, everywhere, there are particles moving faster, there are particles moving slower, there are particles moving about the same as average, and blah blah blah. So that means that for the most part, particles are doing their own thing as they as as it comes out. Like that's how they react to the physical condition that they're in. But so that's why it's important for us to use the average of their velocity, so that we can understand, so that we can link that to temperature and energy. Internal energy of a gas equals 3/2 nRT. So N is the number of moles. Notice that the higher the temperature, the greater the energy, and the greater the number of moles, also the greater amount of energy. Change in internal energy would be change in internal energy, 3/2 nR, change in T. I mean, if you don't change the number of moles in the gas, the change in temperature will equal to the change in internal energy of a gas. Because when we think of an ideal gas, we talk about the internal energy, which is strictly related to its temperature. So we ignore potential kinetic energy at this point. We just consider internal energy. Now, we do have, when we study thermodynamics, we also study about uh, engines. Uh, Heat comes in, generates work, and the unused heat is is released um, in from the engine. Uh, where QH is the heat in a hot reservoir, QC is the heat in a cold reservoir. Of course, if you make the difference between hot and cold bigger, the transfer in energy will be even greater because what happened is heat flows from a hotter object to a colder object. So that's the motion. There's no flow of coldness, there's only flow of heat. And the efficiency of an engine is QH minus QC over QH, which equals 1 minus QC over QH. That will give you the efficiency of the engine. Now, as you notice, the efficiency will never be zero. So you will never have an engine where all the energy that is absorbed is used to the work. Because there's friction, there's entropy. So every time you absorb an energy to the work, part of the energy will be lost due to friction, heat, release. So there's always going to be something lost along the way. And no machine is 100% efficient. In fact, no machine is more efficient than the Carnot engine, which we're going to talk in a little bit. Entropy is the amount of disorder, which is Q over T equals S. So if you want to talk about disorder entropy, you have the amount of heat that goes in, the change in heat over a specific temperature will give you the change in entropy. Um, but that only applies for reversible processes. Once again, no process in the real world is reversible because there's always going to be a change in entropy which will not be zero. So, like a full cycle of engine will give you a change in entropy which is not zero. Sorry, because there's no such thing like that. Entropy in the universe always increasing. Things are not always perfect. Things are always the amount of disorder always increases along the way. All real world processes are irreversible. So if you break a cup, if you let go of a plate and a plate cracks on the floor, you will never get that plate back as it used to be. Because entropy always that's an irreversible process. So during one cycle, the change in entropy in this case will be greater than zero, and that's the way in which things go in everywhere. Right. You can talk about the performance of a heat pump and of a refrigerator by putting QH over work and QC over work, that and so forth. Um, now, talking about the Carnot cycle, um, what happens is that um, there's two images here for the Carnot cycle, and there's pressure over volume and then temperature over entropy. Um, so as we can see on the first case from A to B, gas absorbs the heat, undergoes isothermal expansion, and work is done by the gas. Okay, so in this case, the gas absorbs the heat, but the temperature doesn't change. That's why it says it's isothermal. And the work is done by the gas because the gas is expanding. So the gas is doing the work. Number two, from B to C, gas expands adiabatically, temperature decreases, and work is done by the gas. Work is still done by the gas because the gas is expanding, is pushing against the walls of the container. And then there's a change in volume. Adiabatically, there is that means no heat is absorbed or released, and so there's an expansion that is adiabatically. Now, one thing to point out here is in the pressure volume graph, the isothermal transformations have a more shallow slope, and then the adiabatic processes have a more steeper has they have a steeper slope due to the process and so forth. Number three, gas compresses isothermally, gives off heat. So number three, so the heat is absorbed on from A to B, and heat is released from C to D. So that's the process of an engine. Absorb heat, release heat. Some of it is used to do work. In this case, the gas is doing the work. And work is done on the gas. Why is the work being done on the gas? Because now the gas is being compressed. So now it's not the gas that is doing the work, but it's the gas that is receiving the work, and thus its internal energy is increasing. And a number four, from D to A, gas compresses adiabatically. Once again, adiabatically, there's a steeper slope than D to C to D because it's now an adiabatic transformation, which has a steeper slope than isothermal transformation from C to D. So in an engine, like in this Carnot cycle, for example, um, the gas absorbs the heat from A to B, so there's an isothermal expansion there, and the gas releases the heat from C to D in also an isothermal process. And the adiabatic process are at the ends. Notice one thing, that entropy increases from A to B and remains the same from B to C. And the entropy decreases from C to D, and then remains the same from D to A. So in the Carnot cycle, one full cycle of the engine leads to a change in entropy of exactly zero, and that's not possible. We know that's not possible. This is only possible for reversible processes, but no real world process is reversible. So in that case, a Carnot cycle is in itself an ideal case. And because of that, no engine is more efficient than the Carnot engine. And here we have a picture explaining that. Gas absorbs, heats, and expands from A to B, and then from B to C. Um, Gas expands and cools. So I drew the heat coming out at C. Um, and then from C to D, gas compresses, giving off heat at a constant temperature. So it gives off heat. And gas compresses, heating up from D to A. And like I said before, this would be an ideal case. This would be a perfect engine, I like to say, because the change in entropy would be exactly zero and it would be reversed. Uh, all right. Talking about fluids, we know about pressure, which is force over area, and if we place a object on water, if it's more dense than water, it will sink. If it's just as dense, it would just float. If it's less dense than the water, it will float. Now, the force pushing down the object towards the inside of the water is actually the object's weight. Now, as the object is in water, it's displacing the water. And the water that is displaced exerts a pressure on the object. And this pressure tends to point against gravity, leading to buoyancy. So if you know how much a material weighs due to a spring, and if you place this material with the spring inside the water, you will notice that the apparent weight of the block on the spring will be less because the buoyancy force is also acting against the 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 restoring force, leading to less restoring force in the spring because the buoyancy force is also exerting force up and the weight is down. So that means that with that in case, um, um, buoyancy force is the weight of the displaced fluid. The amount of fluid that was displaced leads to a pressure pushing up on the object. That's what causes buoyancy. Now, Density is mass per volume. Mass is in kilograms, volume is in meters cubed. And pressure is force per area. Pressure is measured in pascals. Uh, one atmospheric pressure, which is the pressure on the surface of the Earth, is about um, 1 times 10 to the 5 pascals. Now, if you place now if you want to measure the pressure at a certain height from the ground, you can use mercury. And what happened is that the pressure, uh, you have mercury in the cylinder, and then there's a container with the mercury inside. And what happened is, as the atmospheric pressure pushes down on the mercury inside the container, depending on how much pressure there is, the mercury is pushed up the cylinder. And the more pressure that there is exerting a force downward on the level of the mercury in the container leads to a higher um, leads to mercury going up higher in the cylinder, and that's called a barometer. That's how we calculate. That's how we discover, and that's how we find out how much pressure there is. Because pressure exerts a force equal in all directions. So if you're at the bottom of a pole, or if you're in the on the surface of the earth, the pressure that the air exerts on you when you're on the surface of the earth, or when you're in the pool, the pressure that the pressure that it exerts on you is equal. The force is equal on all sides, unless you change height on like the higher up you go in on the earth, the less pressure there is. And the same can be said when in a container containing water. The higher up you go, less pressure. But assuming you're not changing the depth or the height, the force exerting on you is the same in all directions. So now we also have the notion of a perfect hydraulic system, assuming a gas or a liquid is not compressible, because that would make it difficult for us to use this equation, because like I said, everything done in physics is our ideal cases. Everything is ideal. Of course, any liquid will compress a little bit. Water doesn't compress that much, so but but we're always talking about ideal cases to make our equations easier. Now, a perfect hydraulic system is that the force per area on one side is equal to the force per area on the other. So if you have two pistons, one with a large area, the other one with a tiny area, there is conservation of pressure as you push down one of these cylinders. Because there's conservation of pressure, you can exert a small force on you can exert a small force on one of the cylinders over over a smaller area, and that can help you push up the bigger piston with a larger area, and that will require less force for you to push the smaller piston down, leading to a machine that facilitates you to support heavy objects. So that means, of course, if you're trying to hold a heavy load on that is over the larger area piston on the left side, you're going to push down on the smaller uh, piston. You will need to go you will need to press it down and move it down a certain distance, while on the other side, conservation of pressure and volume, you would see that on the other side, uh, the load would move up a little bit, um, and so forth. But because we also have conservation of the volume flow rate, we also have conservation, like I said, volume and pressure is the thing. So if your intention is just to support a load you would have to exert you would have to exert a since the cylinder on the right has a smaller area, you would have to exert a smaller force to hold up on the other side the piston with a larger area with a bigger force. So that would save you time and so forth because um, the whole point of a machine is to facilitate motion, is to facilitate what you're doing. So if there's a way that you can exert a smaller force and be able to hold something bigger on the other side, that makes the machine efficient. Now, whenever you have pipes with different cross-sectional areas, we assume a constant volume flow rate, which means that the area times the velocity of the fluid in one cross-sectional area is the same as the area times the velocity of the fluid at the more narrow or more wide cross-sectional area. We have constant volume flow rate, which allows our calculations to make sense. And of course, all of these cases are ideal. So, and of course, if you have a change in height of a pipe or if you have a change in velocity, one thing remains the same is conservation of energy. What is constant is the pressure plus one half the density of the fluid times the velocity of the fluid plus the density of the fluid times g, the acceleration due to gravity, and the h, the height. That remains the same. That equation is derived from the conservation of energy, which allows us to make predictions, which allows us to understand what is going on. Now, with regards to going back to phase change in the material, um, we're talking about fluids, we're talking about gases, we're talking about liquids, solids. So we have three phases. We got solid, liquid, and gas. I know we have plasma, but we're not going to talk about plasma here, ionized gas and so forth. So what we're going to have is that, um, like as you can see, the temperature does not change during phase change. So there's two flat lines from that exist between liquid and solid and liquid and gas. Um, so melting is when you have a solid going into liquid. Freezing is when liquid going to solid. You have a solid, you have condensing, which is when you have gas going into liquid. You have vaporizing when you have liquid going to gas. Sublimation when you have when you have solid going straight to gas. And deposition when you have gas going straight to solid. Um, And as we have the all of the changes that goes on, one thing important to have in mind, especially when we're talking about particles, especially when we're talking about motion around us, we have such thing as macro states and micro states. We use the statistics to better understand what is going on. We know that the universe entropy always increasing, things are always becoming more disordered and so forth. Now, if you have three boxes on one side of a container, here we have a container. The number of microstates there is just one. What does that mean? Well, macrostates is the following. You can have one macrostate, which is three particles on the left side of a container. In this case, we got three there. There's also a possibility of being three particles on the right, so that's a different macrostate. You could have two on one side and one on the other. You could have one on the other and two on the other side, or you can have all three on one side and all three on the other. So these are macrostates. But microstates is when you have it matters which particle are you talking about. It wouldn't matter if you're talking about, for example, which particle is where. Then that it's when you make the particles distinguishable from each other. So especially if you have all three particles in one in one side of the box, the number of microstates is one because they're all three are there. But then things change when you have two particles on one side and one particle on the other, because the number of macrostates there is um, it's still one because you got two on the left and one on the right, but the microstates will be different because what happened there is that you have um, you have an arrangement of three particles, and they can be there's two that will be on the left side, and there's one which will be on the right side. But it does matter which two you put on the left and which one you put on the right. So the number of microstates would be that according to the following equation, 3. So there's three ways you can arrange each of the particles, them taking turns, which one goes to the left, which one goes to the right, and so forth. Now, entropy is a measure of disorder. So you can figure out the entropy of a system by using Boltzmann's constant times the natural log of the microstates, where omega is the symbol for the microstates. So as you can see, there's more disorder when you have two particles on one side and one on the other than when there's three all at one side. So there's more disorder when the particles spread out. So yes, and things are constantly happening and going on, and there's exchange in energy, and there's transfer of momentum, there's pressure, there's forces, and this is a fact that is indeed everywhere. So I've attempted here to give an introduction to thermodynamics and fluids. I hope you enjoyed, and see you next time.